Hello friends, today is succession of my previous video, mechanical properties of a material, stress and strain and their relation. Stress and strain are one of the primary mechanical properties of material. Another way to think about the concept is stress is the load per cross-sectional area, strain is the deformation of the component per original length, and stress can be of three types: torsional, shear, and direct. So what is direct stress? Direct stress is the deformation under tension. We are directly pulling the material and the result is the elongation. Let us discuss the stress and strain curve. In engineering and material science, a stress strain curve for a material gives the relationship between stress and strain. It is obtained by gradually applying the load to a test coupon and measuring the deformation, from which the stress and strain can be determined. Why do we need stress strain curve? Parts or component in real world have to withstand external forces during their lifetime. Products designers should consider these external forces with a factor of safety during product design. Therefore, new parts are designed in such a way that they can withstand these external forces. Stress strain curve represents the behavior of a material when external force is applied to it. Product design engineer use stress strain diagrams for manual calculation and simulation studies to understand a material behavior during actual working condition. To understand the stress strain graph, let us first understand what stress and strain are in the mechanical engineering. What is mechanical stress and strain? Mechanical stress measures the internal resistance exhibited by a body or material due to an external force. Mathematically, mechanical stress is equal to the internal resisting force acting on a body per unit area. So stress is equal to resistive force by unit area, which can be termed as R by A. Strain is a mechanics measure the deformation in a material due to stress. Mathematically, mechanical strain is the ratio to change in length to the original length. How stress strain graph is plotted? We need to perform a material tensile testing on the standard specimen to plot the engineering true stress strain curves using universal testing machine. You can see the photo of a universal testing machine. UTM means universal testing machine consists of two claws. These claws hold and pull the extreme ends of the test specimen at uniform rate. During tensile testing, you need to record any change in length and test specimen applied load at various time stamps until the test sample fractures. These values determine variation in stress acting on the test samples for strain value. Afterward, we can plot the stress strain graph keeping mechanical stress values on the vertical axis and strain on the horizontal axis. Stress strain curve for ductile material. Standard test specimens are used to plot stress strain curve for ductile material using a universal testing machine. During the testing, various observations are taken and plotted on the graph. We will discuss various points of the stress strain graph in detail. Proportional limit. In the graph, you can see the point from O to A. According to Hooke's law, proportional limit is the limit where stress is directly proportional to strain. That means the load applied, the deformation happens. When load is removed, the material back to its zero position. The stress strain curve is a straight line from O to A within the proportional limit. A material Young modulus of elasticity ratio to stress and strain is constant within this proportional limit. The next limit is elastic limit from O to B. The elastic limit of a material is the limit beyond which the material will not come to its original shape when we remove the external force. The material exhibits elastic properties from point A to B, yield point, in the stress strain curve. If the external load or stress goes beyond the elastic limit, the material will not come back to its original shape. Upper yield point, point B, beyond the elastic limit, where the ductile material exhibits plastic properties That means permanent deformation happens. At upper yield point, the maximum stress to initiate plastic deformation inside the material. The strength of material corresponding to point B is known as yield strength. Lower yield point is point C. After point C, the material will increase with a small increase in tensile load or stress. In other words, at lower yield point, minimum load is required to exhibit plastic behavior in the material. Ultimate tensile strength, which is termed also as UTS in mechanical engineering, which is at point D. A material has the ultimate tensile strength at point D on the stress strain diagram. The ultimate tensile strength of a material is the maximum stress a material can withstand before breaking. At point D, necking starts inside the material. The final one is rupture or fracture or breaking strength, which is point E. Point E is the ultimate point where the material fractures or breaks. Stress at point E is known as the breaking strength of a material. Stress strain diagram comparison for a ductile, brittle or plastic material. We can classify most material available in the market into three categories: ductile, brittle and plastic. Each of these material exhibits different behavior when we apply external load. We can understand the behavior of this material by analyzing their stress strain curve. Ductile material has different points of ultimate stress and fractures on the stress strain diagram because they have elastic and plastic deformation. Copper, aluminum and steel are examples of ductile material. Examples of ductile metal behavior: steel sheets regain their initial position up to the elastic limit during the sheet metal bending process. But after elastic limit, the material starts showing plastic behavior and does not come back to its original position. It will continue applying force beyond the elastic limit. The material will break at the fracture point. Curve, you can see the plastic material. It is taking permanent deformation at very low stress. Brittle material breaks with small elastic deformation and without plastic deformation due to the external force. In other words, a brittle material's elastic limit, yield strength, ultimate tensile strength and breaking strength all are equal. Brittle materials absorb relatively little energy before fracture. For example, brittle materials such as pencils or glass breaks suddenly with a snapping sound and small deformation. Ceramic, wood, glass, graphite and cast iron are brittle materials. Similar to ductile material, plastic material also exhibits elastic properties up to the proportional limit. But plastic material requires very less stress compared to ductile material to produce deformation. Plastic materials do not show any work hardening during plastic deformation. For example, if you apply external force to bend a plastic spoon, after the elastic limit, the spoon will not retain its original position. It will be bent forever. So that's all for the stress versus strain and the behavior of ductile, brittle and plastic material. I hope the basic idea is clear on your mind. I will continue with another video related to this mechanical property. Please stay online with me. If you like my teaching, please subscribe my channel and share it to your friends. And don't forget to hit the like button to inspire me more. Signing off, Showman.